Hi everyone, let's start with the next topic, batch distillation with reflux and efficiency. So the learning outcome at the end of this class, you should be able to do the followings: perform calculations on batch distillation with reflux, describe the three types of efficiency in a distillation column, and finally calculate the actual number of stages for a distillation column when given the efficiency using McCabe-Taylor method. So why do we do batch distillation with reflux? Is it simply because batch distillation in a simple still does not give a good separation, i.e. the purity that we get from a simple still with single stage is not very high unless the relative volatility is very high between the two components. So a rectifying column with reflux is used to improve the performance of the batch still. So if you can see the diagram here, you can see that we have a reboiler. So in batch operation, the reboiler have a certain amount of liquid inside the reboiler with, let's say, at time equals to 0, we have the composition of the liquid in the reboiler XB equals to XB at time equals to 0. And then we boil it. So we boil it and the vapor goes up to the column, and then you have the vapor up here where you want to condense and get the liquid product out. So this is the distillate product, and then some of it is returned back to the column as reflux. So this is your L. So the definition is the same. So R equals to L over D and V equals to L plus D. Okay, it's just that the operation is conducted in batch instead of continuous. So you just have to bear in mind the mode of operation is in this case batch. So the XB here changes with time. So if just now starting at time equals to 0, XB equals to XB naught. So after a certain amount of time, let's say time equals to T1, let's say, then the composition of the liquid in the still will change to another composition, let's say XP1 at time equals to T1, and also the liquid remaining in the reboiler will also change the amount. Okay, so if initially you have L1, then after certain time or at the end of the distillation process, you have the amount of liquid becoming L2 with, of course, the bottom composition at that time, the final composition XBF or final. Okay. However, the operation of the batch still and the column can still be analyzed using the same rectifying operation line used in the continuous column, because the material balance equation does not change. Okay. So why do we conduct distillation process with reflux in a batch mode? So there are situations where we need to do the distillation process in batch instead of continuous steady state mode. These are some examples when the capacity of the facility is too small to permit a continuous operation at a practical rate. Okay, so if you want to run the distillation process at continuous mode, it needs to be a large capacity, but if it's too small, then it's not practical. It's a waste of energy, waste of money. So if you just can run it in a batch wise, it's more practical. And sometimes the seasonal or product customer demands require the distillation in one unit of different feedstock to produce different products. So maybe you are catering to different customer demands, different suppliers, and different purity of products is needed for different suppliers. So it's not practical to use a continuous steady state distillation process, because in batch there is more flexibility. Okay, you can adjust the reflux ratio, you can adjust the XD, you can adjust the XB required. Okay, another reason why you want to conduct distillation process in batch is maybe because some new products are to be produced with just one distillation unit for evaluation by potential buyers. It's just like a test product, so you don't want to invest a lot of money in a continuous operation yet. And there are also some reasons, okay, varying compositions of feedstock, varying composition of product, and also maybe the feed contains solids or materials that can plug or foul a continuous distillation column, because if you run it in batch, then it's easier to just stop the distillation process, take out the reboiler and clean up, and then replace it with replenish the reboiler with a new batch of feed. Right, so if you want to run your batch distillation with reflux, there are two most common modes of operation. Number one is to do it in constant distillate composition, i.e. you keep the XD constant. But if you keep the XD constant and also the number of stages constant in the column, because you can't really change the number of stages in the column, you have to vary the reflux ratio with time. And the mode number two is the constant reflux ratio, constant R, also known as constant distillate rate. So distillate rate here is not constant distillate composition, but rather constant D. So if you put R constant, then the distillate composition XD varies with time. So XD varies with time. So which one is easier to be implemented? Okay, let's have a look at your distillation column, batch distillation column. So let's say this is your batch column. So the final stage of the column is a reboiler. So you have some liquid here which you want to boil. Okay, this is your heater. So this one is your condenser, this one is your reflux, this is product. So L, here is V. So let's say you have a certain number of stages in the column. Let's say in this case, three plates plus one reboiler, total 4 stages in the batch column. So you know that R equals to L over D. And then here D, you have the composition XD. So if you put reflux ratio varies with time and you want to keep the XD constant, you have to have a rapidly responding composition sensor such that you can monitor what is the composition of your distillate here. And rapidly responding composition sensor is more expensive and more advanced, more complicated. Compared to, let's say, if you want to put a constant reflux ratio R. So if you want to monitor the reflux ratio to be constant, you just have to monitor the ratio of flow rate L over flow rate D. And it's easier to be implemented for constant reflux ratio R or constant D because of availability of rapidly responding flow sensors, because flow sensors are not really complicated. Flow sensors, you just sense or monitor what's the flow rate of L, what is the flow rate of D, let's say in liters per minute or kg per minute, and so on, etc. Okay, so that's why it said that constant R or constant D is easily implemented compared to constant XD. There is also another mode of operation which combines both constant XD and constant R, which is the optimal control. So in optimal control, both reflux ratio and distillate composition vary with time. So depending on the requirement of the product, so you do this both to maximize the amount of distillate, to minimize the operation time, and of course you want to maximize the profit. Right, so let's have a look at the first mode of operation for batch distillation with reflux, which is constant distillate composition XD. So in this case, the system may be operated to keep the top composition constant by increasing the reflux ratio as the composition of the liquid in the reboiler changes. Okay, so let's visualize your distillation column with the reflux. This is your batch distillation column with reflux, and then you have a certain amount of stages in the column. Okay, The McCabe-Taylor diagram for this case would have operating lines of different slope positions such that the same number of ideal stage was used to go from XD to XB at any time. What does it mean? So let's have your ROL yn plus 1 equals to R over R plus 1 xn plus xd over R plus 1. Okay, so example in the figure. So this is your still with 5 ideal stages, including the reboiler. So reboiler is 1, and then you have 2, 3, 4, 5. So there are the 5 ideal stages. Okay, the numbering may not be conventionally correct because normally we start from the top 1, 2, 3, 4, 5. Okay, but in total you have 5 stages. So let's start with the upper operating line for the initial condition. So first, okay, because you are keeping the XD constant. So have a look at the graph here. So this is your XD for your initial ROL, and you only have 5 stages in the column. So if you just set any number of R, then you will have a certain gradient. So let's say this here is your first operating line. Okay, then you step off from XD. You step off from XD 1 stage, 2 stage, 3 stage, 4 stage, and 5 stage. So this is your XB at that value of R. Then the lower operating line and the dashed line steps show conditions when about 1/3 of the charge has been removed as overhead product. So this one, okay, if you started with this value of R, you get this value of XB. Then you must have a target of what is the final value of XB that you want to achieve. So then keeping the XD constant, you have to vary the value of R. So when you vary the value of R, let's say you move the operating line to here. Okay, this is, let's say, your second operating line, and you start to step off the stages, starting with the same value of XD. 3 stage, 4, 5. So this is your XB at another value of R, where now the slope of the ROL has changed. Okay, so you repeat changing the value of R until you reach the value of XB that you desire. Let's say you want to do the distillation until you get this value of XB final. So you have to keep on changing the value of R, thus changing the, let's say, changing the operating line slope and stepping off the stages to get to the value that you want. Okay, just counting how many stages you are given in the column until you get the final value of XB by varying the value of R. So it's a trial and error. The reflux ratio determination requires a trial and error calculation based on the constant XD and a given XB. So if you want to keep the XD at a certain value, start here and don't move. And given a targeted value of XB, you vary the reflux ratio until you get that value of XB. Okay, so the second mode of operation for batch distillation is constant reflux ratio R. So anyway, we put the ROL here, yn plus 1 equals to R over R plus 1 xn plus xd over R plus 1. So what we do for constant reflux ratio R is you fix the value of R and then let the overhead composition XD vary with time, stopping the distillation when the amount of product or the average concentration in the total product reaches a certain value. So when you fix the value of R, your gradient of the graph is fixed at that value. What is changing is the XD. So what happened is that the operating lines of constant slope will be drawn starting at different values of xd, and the actual number of stages is stepped off to determine the value of xb. So in this case, let's say at time equals to 0, okay, at time equals to 0, oops, I'm sorry, I'm still getting used to this. Okay, at time equals to 0, you start with xd0, initial xd, and let's say you have only 2 stages, and given the value of r, so you have the constant, this is your given gradient. So you step off the stages 1, 2, and then you got this xw or xb at time equals to, not time equals to 0, i.e. the first one that you got. Okay, then at time 1, your xd will change at this point of time. So you start the stepping of stages with the same operating line gradient. See, it's the same operating line for these two ROL. So you step off these stages, because in this case only 2 stages, you step off 2 stages and you got the xb for the second xd, and you repeat until you get the final value of xb. Okay, the total number of moles left in the still is calculated by integration of Rayleigh equation. So you should remember Rayleigh equation from previous topic of this differential distillation. So this would be your Rayleigh equation that we derived previously. However, in this case, we should use a modified Rayleigh equation. So this one, L1 over L2 equals to integration of I guess now this is your still. Okay, so you have xb, and then here, okay, you have xd. So now your y becomes xd, and then your x become xb, because x previously was the composition of the still, and now our composition of the still is xb, and then with respect to xb, and x2 would be the xb2 and xb1. So this would be the Rayleigh equation that you will use for batch distillation with reflux. Right, so let's straight away go to the example. So we do example 1 for constant distillate composition. You can read the question, and actually I have to give credit. This one is taken by from the Learn Chem E page, YouTube channel, Learn Chem E YouTube channel from the University of Colorado. The same example, same question, so I would advise you to go to the YouTube link here to look at the solution, and I've given you all these VLE for ethanol water at the given for this question. You just use this VLE for this question, and go to the YouTube channel or YouTube link to see the step-by-step solution. So I don't need to repeat myself for this, to go through the solution for this, because it's already been shown. Same thing here for the second example for constant reflux. So you just have to go to the YouTube channel here and look at the solution, right? Okay, moving on to tray efficiency. In the previous analysis, i.e. in the previous topics, we have assumed that the vapor leaving each tray was in equilibrium with the liquid leaving the same tray. So we assume that the trays are operating at 100% efficiency. However, in real life, this is not the case, and the vapors leaving the tray rarely achieve the equilibrium composition with the liquid leaving the same tray. In practice, we need to have more trays to get the actual value of equilibrium composition. Okay, so the assumption here is that the vapor and liquid leaving the trays are at the same temperature, for the trays. Okay, of course, throughout the column, the temperature changes Okay, throughout the column, the temperature changes from the bottom to the top. However, from tray to tray, i.e. here, we can assume that the temperature is constant at each tray, except for when there is some exothermic chemical reaction. Okay, the equilibrium with respect to mass transfer, however, is not often valid because of this limitation: insufficient time of contact and insufficient degree of mixing. If you recall, when we use the McCabe-Taylor method for continuous distillation operation, you can see that the triangles are often not of the same size, and sometimes we get not an integer value or for the number of stages. Sometimes the answer is 6.7, 5.5 number of stages. So you may ask, how can the number of trays become with decimal places? This is because we didn't take into account the tray efficiency. Okay, we couldn't be bothered to just modify these numbers into integer because these are just theoretical number of stages. What if the 5.5 and the efficiency is, let's say, 0.5, then you can actually get integer value of, let's say, 11. Okay, so that's why we just for the calculation of theoretical number of stages, we leave it at that. We leave it if it's 6.7, 6.7, 7.8, 7.8. Don't have to round it up to the nearest integer. So now we're going to talk about the different types of efficiency. Okay, so for this case, let's introduce you to 3 types of tray efficiency. I'm sure there are more types of tray efficiency in the books out there, but let's have a look at some basic ones here. So you have first the overall tray efficiency. Overall tray efficiency concerns the entire column. Every tray in the column has the same efficiency. This one is simple to use, but is the least fundamental. So this one is like the normal efficiency definition. So what is normal efficiency definition? So EO equals to, it refers to the entire column. So theoretical number of trays divided by actual number of trays. This will give you the overall efficiency of the column. Whereas the Murphree efficiency EM, E sub M, is efficiency at a single plate. It can be in terms of vapor phase mole fraction, EM vapor, or in terms of liquid phase mole fraction, EM liquid. So you know that vapor phase mole fraction is in terms of Y, and liquid phase mole fraction is in terms of X. What it refers here is the Y composition from plate to plate, and this one is X composition from plate to plate, Yn plus 1, Yn, and Y equilibrium. Here also Xn plus 1, Xn, and X equilibrium. Another type of tray efficiency is local or point efficiency, or also known as Murphree point efficiency, EMP, EM point. So this is the efficiency at a specific location on a single plate. So we will go through the definition of each tray efficiency types in the next slides. Right, for overall tray efficiency, or E overall, as I've mentioned, is defined as the ratio of the number of theoretical trays or ideal trays divided by the number of actual trays used. The overall efficiency have been found to be a complex function of the following: geometry and design of the contacting trays, flow rates and flow paths of vapor and liquid streams, composition and properties of vapor and liquid streams. So, you know, the properties of the vapor and liquid streams, such as the viscosity, density, affects the tray efficiency. Geometry and the design of the contacting trays. You know, trays actually have a lot of types. It can be sieve, it can be bubble cap, can be valve trays. So different type of trays have different efficiency, and flow rates and flow paths of vapor and liquid, because different type of trays here they have different mechanism of how the vapor and liquid flows through the trays, because essentially the trays are just some place to facilitate the mixing between the liquid and vapor phases. So different flow paths and also the flow rates of liquid and vapor will affect the tray efficiency. You can also predict the value of overall efficiency by the following method. Okay, how do you know how to measure the overall tray efficiency? So these are some method, but example of empirical equations are given by previous researchers and industrialists. So this one, for example, the Druckimer-Bradford empirical correlation. So you can estimate the overall efficiency if you know the viscosity of the liquid flowing through the plates. So the O'Connell correlation, for example, you need to know the alpha, relative volatility, and also the viscosity of the liquid. These are all empirical, meaning there's no theoretical basis, but rather you do experiments, you derive a model, then you use it to estimate the efficiency. Okay, next type of efficiency is the Murphree efficiency, E sub M. So the Murphree efficiency is based on semi-theoretical model, assuming that the vapor between the trays is well mixed. So what does it mean is that, okay, all the vapor leaving the tray is having the same composition, and all the liquid here having the same composition, here have the same composition, meaning the composition at any point across the trays are the same. Okay, that's the idea of Murphree efficiency. So Murphree efficiency can be based on either liquid phase or the vapor phase. So for a given component, it is equal to the change in the actual concentration in the phase divided by the change predicted by the equilibrium condition. So what it means is that, okay, this is the theory at the bottom here, and the upper one here is actual. So in theory, you would reach the equilibrium concentration at that plate, okay? The concentration, Yn star, is the concentration of vapor in equilibrium with liquid leaving the tray end to the downcomer. But however, the Yn here, the actual concentration of the vapor leaving the tray end, will not be the same with Yn star. So in actual, Yn is less than Yn star. So that's why that's what it means for this point here, okay? The change in the actual concentration in the phase divided by the change predicted by the equilibrium condition. So this is it. The difference in the concentration divided by the theoretical difference of the concentration between the two, between this point and this point, these 2 points. Okay. By convention, EM is defined using vapor concentration. So that's why in this definition here, I'm using Y instead of X, because we are referring EM using vapor concentration based on the vapor phase. So that's why we are just looking at the Y instead of X. Another type is the local or point efficiency, or Murphree point efficiency, E sub MP, Murphree point. Okay, so for Murphree point efficiency, compared to the previously Murphree efficiency without the point, it's just that in this case now, it no longer assume constant or uniform composition throughout the plate. It assumes, in this definition of point efficiency, it says that this is the composition at this point, and then this is the composition at this point, and this is the composition at this point. The same point in the column rather than across the column. Previously, we are assuming same and uniform composition across the column, left to right of the column. But for point efficiency, we are assuming different composition at different points in the column. So if you were to move to this side, you will have different y, different xn, and different y sub n plus 1, and so on. So if you want to have an average composition, is you have to have the composition here, the composition here, composition here, and here, and here, and you take the average. That will give you the composition of the liquid and vapor phase in across the plate. Okay, when does the point efficiency become significant? Okay, in theory, for small diameter column, the point efficiency does not make a lot of difference. So point efficiency is the same with Murphree efficiency, because in small diameter towers, the vapor flow sufficiently agitates the liquid so that the composition is uniform across the tray. Okay, so but for larger diameter column, an incomplete mixing of the liquid can occur, because some vapor, if you have a larger diameter column, so you have a longer length from the left to right of the column, so the vapor contacting the entering liquid, so let's say the entering liquid enters at this point, and then enters and then leave at this point, and the vapor coming up, okay, across from the bottom of the plate. So the vapor coming up that is in contact with this liquid will have a richer vapor composition compared to this vapor in contact with the leaving liquid. So that's why in this case the Murphree point efficiency is significantly, it's quite considerably different from just the Murphree plate efficiency. Okay, you can relate Murphree and overall efficiency using several methods. One method, an easy method, is if the equilibrium line is straight, i.e. if the equilibrium line is just y equals to mx, then m is constant, then the slope of the operating line L over V is constant. You can use this equation to relate EO and EM. Okay, so M here is the slope of the operating line, and V and L here is just the vapor flow rate and the liquid flow rate, the ratio of vapor flow rate and liquid flow rate in the column. Okay, so otherwise, if you don't have such straight line and you don't have the constant liquid to vapor flow rate, then you need to use graphical method. Alright, as mentioned, if your equilibrium curve does not satisfy the y equals to mx line, it is instead a curve, then to relate Murphree efficiency and overall efficiency, you have to use the graphical method. So let's say given a known value of EM, you can use the Metcalfe-Taylor diagram to determine the actual number of trays. So previously you have seen this definition of EM, which is the difference in the Y composition, the composition of the vapor phase from plate N to plate N plus 1, divided by what would be the equilibrium composition of vapor in plate N minus the composition of vapor in plate N plus 1. Because here you see, previously you already derived the operating line equation. Okay, so you should know where is yn plus 1 and relate to the y previous n and so on. Okay, let's say using the equilibrium data here, you can draw an effective equilibrium curve using the Murphree efficiency by replacing the equilibrium composition with okay, let me rephrase that again. So if your tray is 100% efficient, you would reach the vapor composition, you would use this actual VLE curve. However, if your Murphree efficiency is only 60%, meaning instead of from, let's say if you have this x here, xn, x or something, and then if your tray is highly efficient, you would reach to point C to get your yn star. However, if it's only 60% efficient, you would only go 60% of the way. 60% of the way you cannot reach up to yn star. You only reach 60% of the way. So you can just draw a line going through the point B where the ratio of this to this is 60%. Okay, so if you have this one is xn, then xn, this one will give you, this one is xn, you will get yn plus 1 based on the operating line equation. And for equilibrium relation from xn, you should get yn star, but because your tray is not 100% efficient, it's only 60% efficient, you only go until this point yn, and this point here is divided by this point is 60%. And take note that the reboiler stage is not subjected to tray efficiency. Thus, the equilibrium curve is used. The actual equilibrium curve is used here. Okay, you don't have to stop here, but rather you go all the way to the actual equilibrium curve to get to xb or xw. Okay. Okay, let's do an example for the relationship between overall efficiency and Murphree efficiency. Let's say for a stripping column used to remove traces of a slightly soluble organic compound from water, the equilibrium line is given y equals to 120x and the L to V ratio is 15. If the Murphree plate efficiency is 0.4, what is the overall efficiency of this column? So from the information given, you have EM equals to 0.40, capital M. M equals to 120 and the L over V is 15. So you can just use the equation. You can just use the equation that we have just now to calculate the EO. So EO equals to something. Okay, now you have M, V and L. So this is your M, 120. L over V is 15. So your V over L is 1 over 15. So MV over L is 8. So using this equation, EO equals to blah blah blah. Then you just plug in the numbers. So EM is 0.4, MV over L is 8, then you get EO is 64. So you have the overall efficiency of 64%. Okay, let's do another example for Murphree efficiency and actual number of trays. Let's say you are given a saturated liquid feed of 200 mol per hour at the boiling point containing 42 mol percent heptane and 58 mol percent ethyl benzene is to be fractionated at 101.32 kilopascal absolute to give a distillate containing 97 mol percent heptane and a bottoms containing 1.1 mol percent heptane. The reflux ratio used is 2.5 and the Murphree tray efficiency is estimated to be 0.55. Determine the following. So the first one is just to do the material balance to get the mole per hour of distillate and bottoms. B is to calculate the ideal or theoretical number of trays. And C, the actual number of trays needed at the given Murphree efficiency. And finally, the overall efficiency EO. Okay, let's do part A, material balance. This one is easy. It's usually the warm-up question in any distillation problem given. So you have a feed of 200 mol per hour and the feed composition is 0.42. Then you have a product. So the distillate with given xt is 0.97, and you have this is your reboiler, then your bottom product, and xb is given 0.11. R is given as 2.5 and E of M is 0.55. So let's do part A. You want to find what is D, what is B. So do overall material balance F equals to D plus B. 200 equals to D plus B. So B equals to 200 minus D. And also you can do component balance Fxf equals to Dxd plus Bxb. So 200 times 0.42 equals to 0.97 D plus 0.011. Sorry, this should be 0.011 B. So you solve these two equations to get D equals to 85.3 mole per hour and B equals to 114.7 mole per hour. So part A is done. Okay, so for part B, you have to calculate the theoretical number of stages. You know what to do. You plot the BLE data, ROL, Q line, SOL. So let's just do it again this time. So this is BLE data. You should plot it, and then given the R value, R equals to 2.5, you can plot yn plus 1 equals to R over R plus 1 xn plus xd over R plus 1. So yn plus 1 equals to 2.5 over 3.5 xn plus 0.97 over 3.5. Simplify the equation equals to 0.714 xn plus 0.277. So this is your ROL. So for Q line, Q is given as a saturated liquid at its boiling point. So Q equals to 1. It's a vertical straight line passing through the feed composition. So it's essentially x equal to xf equals to 0.42. So we have, this is your Q line equation. Okay, now that you know your ROL and Q line, so you know the points for your ROL would be XD. XD in this case is 0.97. 0.97 is 1 point. So you can try to put that one here. So that is 1 point for your ROL. And also the equation just now, when x equals to 0, y equals to 0.277, so you can mark 1 point here at almost 0.28. So what you have is 1 point here, 0.97, and then try to draw the graph here. Okay, might not be as accurate, but you can try to make it more accurate. So that's your ROL. So your Q line is a vertical straight line passing through x equal to 0.42. Okay, so this is your Q line. So your XB for SOL, XB is 0.011, 0.011. So that will be here. So from this point, you draw a line. So that will give you your SOL. This is oh no. We're getting used to drawing on this thing. Oh no. Okay. Should be a straight line there, yeah. Okay. This is your SOL, Q line, ROL. Where is the picture gone? Oh my god. Okay, just pretend it's a proper SOL. You should do it better. So you step off the stages starting from XD. Do it properly, don't do it like this. What I'm trying to say is that for the theoretical number of stages, you step off until you touch the blue equilibrium line, because it's assumed to be 100% efficient. So you count from number 1, number 2, number 3, number 4, number 5, number 6, 7, 8, 9, 10, 11, approximately 11 ideal stage. Okay, but please don't do it like this. Please use the proper ruler, straight line, vertical and horizontal. Okay, so that is for part B, to calculate the number of theoretical stages, including the reboiler. Okay, so for part C, you are asked to take into account the Murphree efficiency. So what you do is, this is given the VLE for the blue line. Okay, you plot your ROL, SOL and Q line as previously. So let me just try it again this time. That's 1 point for the ROL. This is another point for the ROL. So I try to connect these 2 points to get one nice straight line. Come on. Okay. ROL, and then your Q line equation passing through 0.42, and then your SOL. Okay. Okay, when you have the Murphree efficiency, EM oh my god, EM is 0.6. What it means is that instead of going all the way from this point to this point is 100% efficient. I try that again. Okay, this point to this point is 100% efficient. But if you have 60% efficiency, you only go through all 60% of the way. 60% efficient. Okay, so you can either measure to be accurately 0.6 times the distance from here to here, or you can use an eyeball method to just estimate the pseudo equilibrium curve. I have to draw the ROL again because it disappeared. So I said that's your ROL. So what you have is, let's say this one is your 1 point of your pseudo equilibrium curve, 60% of the way, 60% of the way, 60% of the way, 60% of the way. Okay, so you connect this curve. Okay, so the green line here is the pseudo equilibrium curve, i.e. it's just 60% of the way between the operating line and the actual VLE curve. Okay, so if previously you step up the stages until you touch the blue line, right? But now you cannot. You have to step off the stages only until you touch the green line. So what you do is step off from XD, you try to step off. Okay, you step off until you reach the bottom. Please step off properly. So you can see that if you take into account the efficiency, you will require more number of stages. Okay, you can count lah. Okay, if assuming this is a correct line drawn properly, then you can count the number of stages: 15, 16, 17, 18, 19, let's say 20. So if you take into account the Murphree efficiency of 60%, you will end up with actual number of stages is approximately 20. But take into account that the last one for the XB, you have to touch the actual VLE curve, not the pseudo equilibrium curve. So let's say after taking into account the 60% Murphree efficiency, you've got 20 stages. And in B, you have 11 stages, right? Ideal. So this is ideal stages. This is actual number of stages. So this will give you the answer to part C. So for part D, the overall efficiency, EO, is 10. Number of ideal divided by number of actual. 11 over 20 will give you 11 divided by 20 is 0.55. So overall efficiency is 0.55 for this system. Okay, previous graphs was a graph that I tried to show you how to draw if you take into account the ROL, SOL, and to draw the pseudo equilibrium curve. But if you were to use Excel, this is what you will get. So I just want to show you. This is the y equal to x line, and then this one, the yellow line here is ROL. This gray line is Q line. This one is your SOL. Because if you draw using Excel, you get more accurate in terms of, especially at 0.011 here. Okay, and to highlight that this is your pseudo equilibrium curve, 60% of the way between these two lines. Okay, so this to this, the ratio of, let's say this is x, this is y, the ratio of x to y is 0.6. that is your Murphree efficiency. Okay, so if you have a nicely drawn line here, you can try to step off the stages starting from XD until XB and calculate what is the ideal number of stages if you step from this line to this line versus if you step from this line to this line. Okay, so you have to do it on your own. Try to do it to actually get it and understand the concept.